Good morning, everyone, and welcome to the Central Region Guest Speakers Series. Today we have a pretty interesting talk. It's the anatomy of a disaster, the Marshall Fire. With us today, our presenters are Bruno Rodriguez and Paul Schlatter. Bruno is an IMET with the Boulder office. He's also a fire weather focal point there in Boulder. He's been in Boulder for almost a year, and prior to that, he was at the forecast office in San Diego since 2018. Bruno was working the day shift on the fire marshal, but oddly enough, Bruno is on a big fire currently in Idaho doing his IMET duty, so he will not be joining us today. But we do have Paul, and Paul is the SU at Boulder. He's been in that position for 6 years. He's got his start in the Weather Service with the Warning Decision Training Division down in Norman almost 20 years ago. And from 2011 to 2016, he worked with NWS headquarters, in which he was the Deputy Chief of Staff and Acting Chief of Staff. And he's also been a past president of the NWA. Paul will be presenting, like I said, the Marshall Fire, which was one of Colorado's costliest wildfires in history. It occurred during an extreme downslope wind event on December 30th, 2021. And he'll go over the science behind the event as well as some DSS provided there by the office. Just a reminder that this is recorded and that we will provide this to everyone afterwards. And I'll also be monitoring chat, and you can also raise your hand if you got questions. And with that, I will throw it over to you, Paul.
All right, thanks, Greg, and good morning, everyone. Happy to be here with Central Region Guest Speaker Series. Thanks to Randy Graham for allowing me to speak here. Gosh, I really do wish Bruno was with me today. We gave a much scaled down version of this at NWA. We had about 18 minutes to present it. Today, we'll be able to go into much more detail, especially on the science and service side of this disaster. So let's just get right in it here. Once this video plays. Okay, so just a quick overview of what the event was and just how damaging it was. Almost 1,100 homes were totally destroyed. About 149 were damaged. I guess in some sense, luckily, but it was still tragic that there were just 2 fatalities throughout the entire event, given how fast the fire moved from house to house and neighborhood to neighborhood. 7 commercial properties were destroyed, 30 were damaged, and over 600 million in losses so far, making it the costliest in Colorado history. Let me move on. Let me see here. There we go. Okay, so what I'm going to talk about today, we'll discuss the antecedent conditions that led to this disaster, the science behind the winds, a short but pretty interesting wind analysis that we were able to piece together during the fire, and then if Bruno were here, he would talk about the last part, but I will cover that, no problem. The operations before, during, and after the fire, especially with a focus on DSS. So first, the antecedent conditions. Well, we were in significant drought. We were D3 pretty much that entire year. From late summer on, really, we were about D3. Part of it was long-term, but in general, the Marshall Fire is right where this crosshair is in the state of Colorado. It was, squarely within D3 right before the event. The Colorado Climate Center also has a standardized precipitation evapotranspiration index, SPEI. Again, the Marshall Fire is right at the crosshairs there. And values less than -2 are about as high-end anomalous as it gets, just indicating warm, very warm and very dry conditions leading up to an event. And this pretty much off the charts. It was maxed out in terms of warm and dry near where the fire started. But that wasn't all. In early 2021, it was actually much above normal precipitation through the first half of the year. About 4 inches above normal precipitation for that time frame. That's, of course, once May hits, everything greens up around here. Grasses start going crazy, especially if it's a wet spring, and it was. And so all nice, lush, and green in June. Even July, this is within a mile or so of where the fire started, give or take. And it's still lush, green, really tall grasses. There were flowers and growth that hadn't been seen in many years because of how wet the spring was. So those fuels grew like crazy. And then when the warm and dry hit, dried out like crazy. And that's what happened the last half. So it went from really wet to super warm and super dry. This is for Denver, this particular chart, with average temperature on the left, precipitation on the bottom. So warm and wet years will be top right, cool and dry bottom left. And then, of course, for fires, warm and dry are in the top left quadrant here. And if you see 2021 stands out as both the warmest and the driest, at least for Denver, which isn't too far from Boulder. If we looked at Boulder stats, it was actually the 6th warmest and 15th driest overall in the period of record. And that's roughly over the last 60, 70 years that we did this, or the Colorado Climate Center did this. So Boulder was kind of in the same boat with just a record-breaking warm and dry, essentially, together for the last 6 months of the year. So that was the conditions leading up to December 30th. Let's talk a little bit about what the setup meteorologically was in terms of the mountain wave that's set up. And so we'll do a little bit of science here, some fun science. Here's the schematic, traditional schematic from Comet on, how a mountain wave works. These are streamlines, and basically a strong inversion. For a mountain wave, you really want a strong inversion to set up, about 3,000 feet or so, give or take, above the top of the ridge line. And in essence, what that does is that kind of forces the winds through this narrow channel. And then when it comes down the lee side of the Rockies, severe winds occur right at the base of the foothills. And then, assuming there's no wind shear above the inversion, that allows these real strong upwind vertical wave propagation to develop, which can lead to breaking waves, hydraulic jumps, and a rotor setting up. I mean, this is the mountain wave. The rotor is pretty much the same manifestation of the mountain wave, where very little winds occur underneath the rotor. They get deflected above, and then on the other side of the rotor, a wave pattern can set up sometimes where there's strong winds interdispersed with very little winds. But by far and away, the reason these are so significant is just at the base of the foothills, those severe winds can really get going. And if you put a fire in that environment, look out. So why is the Colorado Front Range so unique? Here is a topographic relief map where showing the higher elevations in white. City of Boulder and the lower elevations, the plains, are kind of in that grayish bluish color. And so in this general area of the rectangle, there is an unbroken ridge, roughly 100 miles long, averaging 12,000 feet high. So that's 7,000 feet higher than the plains that are around 5,000 feet. But this barrier is totally unbroken. That's what makes it so unique. You'll see that winds from the west or slightly north of west are perfectly perpendicular to this ridge. And so that's important for cross barrier flow and the development of mountain waves, so all this comes together to make the area inside this rectangle the perfect location for high-end mountain wave development and extreme winds right along the corridor of the foothills and then the plains just to the east of it. So really from Boulder to Golden and then north to Lyons, this little corridor here always sees mountain wave developments every winter. So talking about stability, as I mentioned in the original graphic with the mountain wave, it's really a Goldilocks analogy where you need the right location and the right strength of the stability to get the response of a mountain wave development. So let's say in this particular case, these are isotropes. If the stability, recall from whatever class that was, maybe thermodynamics or maybe dynamics. It was probably dynamics way back in the day. When these are closely packed together, that's stability. So let's say that it's really shallow stability, right, and not even that strong. You get very little response on the lee side. Down in the lower left, unstable, pretty far above the ridge top, and then very stable, with the tropopause. You really don't get any lee side response to any mountain wave development. In the lower right, it's unstable throughout the depth of the atmosphere. You also get very little lee side response to flow over that ridge. However, if that stability is perfectly situated and strong, such that it's about 1 to 2 kilometers, so that's 3,000 to 6,000 feet, more or less, above the top of the ridge with westerly flow going over it, you get a major lee side flow increase. You get wave development. You get wave development downstream. You can get hydraulic jumps, which are, severe winds crashing to the surface occasionally. That does happen in many mountain wave events. But in general, this is the type of setup you're looking for. Stability right around that ridgetop area, squeezing the flow through that channel, and then emerging on the lee side with extreme winds. So what were the soundings actually showing? Well, thankfully, we actually had helium back then, so we had a sounding. And you'll note that the 12Z sounding on the day of the event does show an inversion actually above 500 millibars. We don't really use rule of thumbs, but in general, our office looks for inversions that are around the 550 millibar region, because that's that sweet spot above the ridge top that we would look at. But so this isn't a home run inversion for a mountain wave, but it is a pretty good one still. It's just a little higher than normal. On the Grand Junction sounding, you'll note that inversion is down to 500 millibars here, getting a little bit better. Note the flow. So there's the inversions. Note the flow aloft above the inversion. It is very strong. It's about 110 knots, but there's almost no wind shear whatsoever on either of these soundings. Favorable for the wave development, because wind shear above the inversion can destroy the mountain wave if there's too much of it. But in this case, as a forecaster, we're confident that wind shear is not going to be an issue. If a wave develops, it's not going to get destroyed by wind shear aloft. And then finally, these are pretty strong winds right underneath the inversion that are going to squeeze through that channel between the inversion and the 12,000 foot ridge to the west. There's about 80 knots, 70 to 80 knots on at least the Denver sounding when looking at this. So pretty good setup. But the fly in the ointment was that inversion. Was it too high to get the winds all the way into the populated areas of the lower elevations? So looking at, this is mainly just kind of an analysis field of the 300 millibar jet, showing a slowly exiting polar jet with northeast Colorado. You can infer in the left entrance region of the jet, which is favorable for downslope winds because you're in the subsident part of the jet. At 11 a.m. when the winds are really cranking, that jet's still kind of there. You can infer, again, it's pretty strong mesoscale sinking in the left entrance of the jet. And that jet still just kind of hangs around. I know the stronger winds lift out a little bit, but the jet hasn't really moved even through 5 p.m. At 500 millibars, just kind of showing that we're at the trough axis had moved through. And it's just kind of flat westerly flow. Again, that's exactly what you want, especially if the trough had already moved on. You want warmer air to filter in from the west to create that inversion around 500 millibars. But suffice to say, this was a pretty good setup. Straight westerly flow, which is good for mountain wave development, and then real strong flow, about 80 knots at 500. Just looking at just 550, where we want that inversion to stand out, and even though the soundings didn't capture this, these are mostly analysis fields, and it does show that throughout the day it warmed significantly at 550 millibars. I mean, 13 degrees Celsius over the course of about 24 hours. That's pretty impressive warming, right in that layer that you want an inversion to set up for a mountain wave. So we think that this was one of the main ingredients that maybe the soundings didn't pick up on, that really shows how that inversion developed throughout the day and led to a strong mountain wave development. So let's piece this together to show what it would look like superimposed on our local area right at the base of the foothills here and the Rockies. So it's the same graphic essentially. We're just putting places to it. So that stable layer was in place. Boulder is right at the base of the foothills. Highway 93 runs north-south through Boulder, and it's also it's a north-south highway. So it is used to those strong downslope winds because it's perfectly located about 2 to 3 miles ish west of the terrain or east of the terrain gradient, right where the strongest flow develops. That's also where the fire started, right along Highway 93. So that is the place where the strongest winds typically occur. And then for the Marshall fire, a rotor, and I'll show plenty evidence of where the rotor set up. sets up kind of along the Lafayette Broomfield area, so that Superior and Louisville, Highway 93, they're kind of in the jump region where those extreme winds typically are at the surface, and then much lighter winds just east of there associated with the rotor. So this is the schematic. What did it look like in person? That is what the fire and mountain wave / rotor, however you want to characterize it, looked like in person. So we're looking towards the south at the fire. So this is extreme west winds fueling the fire. The fire's off to the right. You can't really see it, but it's the extreme winds are still blowing well to the east, and then it reaches the rotor and wave. There's some actual cumulus development, rotor clouds on top of it, and then it descends the other branch of the rotor with weak winds right in this area. We'll play that one more time, just to give you a sense of, we're actually seeing that schematic play out in person because there is the tracer of smoke filling the entire flow of this particular event. I think you might even see some dust somewhere. Oh yeah, right here. There was actually dust picked up as well, where that strong winds are, where those winds are. Another schematic. This is a different angle. This is taken from downtown Boulder, so it's actually looking a little north as well. Just a little bit closer and a little more better time lapse of the actual rotor clouds developing on top of the rotor. The real strong wind, the fire's again just off to the right. You can't really see the fire because it's blocked by this building and it may even be out of the display, but showing the extreme west winds going into that rotor. Let's go move on here. All right, so that was kind of the science behind it, the mountain wave. How do models do in mountain wave? And forecasting here, as long as we have, it's typical. They don't do very well. The nature of the mountain wave, it's so small scale. Not only do you need good horizontal resolution, you also need to have really good vertical resolution. Ensemble output isn't going to get you there because the ensemble members suffer the same as all of the other members that make up the ensemble in the first place. They just can't resolve it, so you're not going to get those strong winds even in a few ensemble members. So it's not surprising how poorly the models do. The HER did a pretty good job with this one. I'll dig in quite a bit, at least give you an overview of what we were looking at when we were forecasting this event, primarily using the HER, because that's the one model we can typically rely on to at least help us with these things. The MBM 4.0 was not useful at all. I'm not going to show, I only show one example of it, but I will say that 4.1 with its better bias corrected wind scheme was much better than 4.0. Here is the 4.0. This is the only example I have of 4.0 because it didn't help a whole lot. This is roughly a 56-ish hour forecast, 56, maybe between 2.5 days, basically. That far out, none of the models had much of a clue of a big mountain wave event, so it's not surprising that the 4.0 did either. The Marshall Fire started right here, and it's showing about 10-knot winds. This is very typical. If you forecast along the Front Range of Colorado long enough, this is what you see. It's always a question: are these winds at ridgetop going to extend east to Boulder and the populated areas of west side of Metro Denver? Are they going to get out of the foothills? That is the forecasting challenge. That depends a lot on how much subsidence aloft there is. It depends on what the wind shear aloft is, and it also very much depends on that inversion. How strong it is, where it's located, is it at the perfect height so that the winds can emerge much stronger on the east side. I will also say that 4.0, even when it ingested, once it gets to the HER, once it ingests the HER, it still didn't do very good. It had gusts maybe to 30 knots tops across this general zone where the fire was. 4.1 did a lot better, and it's because of the bias correction. So talking about the HER, roughly 18 hours, it really started picking up on the potential 18 hours out. This is a cross section through the ridge to the west of Boulder, showing extreme winds at the base of the foothills, just like the schematic shows. Depression in the isotropes, just like the schematic shows. So it's picking up on the potential starting right around there. I'm pretty sure, and it was consistent. That was another huge thing, is that from about the night before, around 0Z, so 18 hours before the strongest winds really got going, 18 hours before the fire even started, the HER was saying, okay, you're going to have extreme winds making it to the lower elevations, and it was saying that every single new run, it was saying the same thing. Sometimes you'll see the HER jump around where the winds extend east, and sometimes they stay in the foothills. This was good in that it was really consistent. And I also think that's why 4.1 did so well, is because the HER was really confident in it as well. So this is probably the best representation of what the HER forecast for us. This was I believe this is the midnight run, or just after, sorry, 11, it was 11 p.m. local time. Notice it shows that wall of wind associated with the rotor just east of the Rockies. The fire started right here. So it's doing a pretty good job. This is sustained winds of about 50 or 60. That's not too bad. You also note that it picks up on the wave pattern. Watch downwind. See that? So it's picking up that a pretty significant initial mountain wave and rotor setting up right where the fire starts with waves downstream. This tells us as forecasters that the HER has a pretty good handle on how that mountain wave is going to set up. It did okay for this area, and it was consistent. North and Larimer County up here, those winds did not materialize, so take it as a grain of salt. We also don't typically see very strong mountain waves develop in this region. It's just it's a much harder place to get the extreme winds, but this corridor, the HER got it. So looking at the HER was the best. It still wasn't perfect, and it really does start with the analysis fields. This is 18Z, right when the winds were cranking. The fire had just started and really spread like crazy. And this is gust potential around 60, 65 knots. They were actually gusting around 90 knots right around this time, right where the Marshall Fire started in this general area. Again, the HER was just insistent, even in the analysis fields, that there were extreme winds going on in Larimer County. We just didn't really see that. At 22Z, the winds were still going really strong. The fire was still burning the heck out of Superior and Louisville. And you'll note that the analysis field only picks up about, this is gust potential again, about 55 knot gusts. It was gusting to 70 at least still by this point in this general area. So the analysis field suffered. It's no surprise that the forecast itself didn't do so great. So this is 18Z from 2 days before the fire really got going. This is the furthest out the HER goes, 48 hours. And every model, global, didn't matter, the 12 kilometer NAM, the 3 kilometer NAM nest, all pretty much showed the same thing. These are max wind over the past hour. The Marshall Fire started here. So this is 15Z on the day of the Marshall Fire, 16Z, 18Z. 18Z again, that's like the fire was really going then. And it's got wind gusts of about 10 knots. That's about it. Every model showed the same thing. Most likely because it's not resolving the inversion and not forcing the winds further east. A neat product that I encourage you to look at if you're into fire weather is the wildfire potential that's available on the HER. And that did kind of show it. So that incorporates dryness. It tries to handle fuels, and it does wind. So wind, dryness, all that good stuff. And it even with that, it is showing a high end potential for wildfire spread, even without the really strong winds yet. So 0Z run, as I mentioned earlier, that's when the model really dug its heels in and said, hey, you're going to have a pretty significant event, mountain wave event set up. And it started showing it from the 0Z run 18 hours before, and it kept doing it each hour. So it's picking up on it. By 17Z, it's got 50 to 55 knot winds. The wildfire potential now, with the winds as extreme as they are, all pegged at the highest levels by that particular point. But it was all about the consistency. Here is, okay, so this is showing the consistency. Not that this is the best verification, but it was the analysis field at 18Z showing those strong, 70, 75 knot gusts right where the fire started. These are 4 successive runs of the HER, the 11-hour, 10-hour, 9-hour, 8-hour forecast run of the HER. All kind of saying the same thing. You're going to have an extreme mountain wave set up across eastern Boulder County, where there's going to be a sharp drop off in the winds where the rotor sets up, but that west of that rotor, you could have issues if the fire starts there because of how strong the winds are. So these are challenging. Mountain waves are too challenging for models, and vertical, horizontal doesn't matter. The 4.1 did better because it ingested the HRRR, and also that improved bias correction scheme. It did a lot better. So the forecasting challenge always is, as I mentioned, how far east are those winds going to reach? And oftentimes the HRRR is right. Sometimes it false alarms on the east winds. It's always kind of it's a difficult issue, but we really key in on when the HRRR is consistently showing the winds extending east. So what were the weather conditions? Starting at 11 a.m., and I'll do a time series of the winds, but this kind of gives you a setup of how narrowly focused those winds are. So it started at 11 a.m. as gusting to 81 in South Boulder. The fire started here. Here's the outline of where the fire spread over the next 5 to 6 hours. Once it started just after 11 a.m. It was gusting to 99, 105 miles an hour in these areas. Here's Highway 93, as I mentioned. So okay, so give you more orientation. Here's Boulder, Highway 93 where the fire started, and then Superior and Louisville. At 12 p.m., still gusting well over 80 to 90 miles per hour, even 100 miles per hour to the south of the fire. The fire had already made it to the west side of Superior, right on that wildland urban interface, kind of in this area. Notice to the east, winds are really light, northeast, gusting 10, 20 miles an hour underneath the rotor. And sometimes a little east of the rotor where the flow actually reverses direction on the east side of the rotor, so that you get light east winds. Obviously, this is good. If the fire were to ever get to this area, that's a good thing. The winds are actually going to keep it from extending too far east. But anywhere west of that rotor, it's 100-mile-per-hour winds. You can't fight that fire. There was no stopping it. At 1 p.m., same story. Maybe the rotor just a little bit better to find in the surface obs, and actually got a 41-mile-per-hour gust out of the east on the east side of that. But in general, it was still gusting 70 to 100 miles per hour at 2 p.m. That was at 1 p.m. At 2 p.m., same thing, still gusting 80 to 90. Where the fire was really going, erratic winds gusting to 70, right at the base of the rotor and on the ascending branch of that rotor, where that was, and still light and east, northeast, or even southeast on the east side of the town there. 3 p.m., still gusting at 80. The fire did begin to slow its eastward progress just because it was in that part of the rotor where there was still weak winds. 4 p.m., the winds were still 70 miles per hour gusting. The rotor hadn't moved in 8 hours by this point. So checking the max gusts, very typical in a mountain wave event. It's localized within a few miles of the terrain grade. So all the max gusts are kind of within this corridor. Anywhere it's 80 to 115 miles an hour, basically, is what it was gusting to right there. And then east of that, the gusts weren't as severe because you're out of the shooting flow, the extreme flow, and on the east side of the rotor. What was unusual for this particular event is that mountain wave didn't move for 10 hours. And for those 10 hours, it was gusting 70 to 110 miles an hour. Much more often, both in the literature and just empirical evidence forecasting here for as long as we have, those mountain waves typically don't stay put for very long. What I mean by that is that they may blow like crazy, like it is here, for an hour, maybe 2 hours, and then either they break down because the hydraulic jump is occurring, the stability changes, there's wind shear loft. They can propagate east with time and before another one develops. So sometimes you can get an hour or longer break in the extreme winds where it's almost calm, dead calm, because the mountain wave has either moved or lifted. It can do a variety of things, but not in this case. It was 10 straight hours of extreme winds along this corridor. So let's zoom in a little bit on this corridor. So again, here's the outline of the Marshall Fire. We had a really good wind ob, South Boulder, National Renewable Energy Lab, and then at the famous, this is our most famous wind sensor. It's at CDOT's Colorado 93 and 72 intersection right here. Also have at my house a really good wind sensor, and then further east, 9 News is a buddy of mine, Corey Reppenhagen, also has a really good wind sensor. We're almost in an east-west line, so this particular time series is really a cross section through the mountain wave itself. I'll also show a time series of the north-south, you know, right in the heart of the worst winds of the mountain wave. But in general, west of this line, gusted over 80 for about 10 hours. Kind of in between there, where on the ascending branch of the rotor, it was 40 to 80 miles per hour. And then east of there, probably less than 30 miles per hour. And often the winds were east to east northeast. So this is a 9-mile stretch. That's it. That's one of the reasons it's so difficult for models to be able to handle this. That you're going from 80 to 100 mile per hour gusts, and then 9 miles to the east of that, it's the opposite direction and light and variable, or maybe just 20 to 30 mile per hour winds. Keep in mind when we see the time series, the fire started between 11:20 and 11:40 a.m. Right here is where the fire started. Okay, so the first time series is that north-south cross section right through the extreme winds. Of course, I did that. There we go. The blue dots are that's typically our strongest winds. Period. Anywhere in Colorado, at least in lower elevations, are at the blue sensor, and you can see it really picked up around 8 and made it 10 to 11 hours. There wasn't really a time when gusts weren't at least 60, and most of the time they were 80 to 100 plus. Not far away from where the fire started, the green line, same story. 50 to 80 mile per hour winds, gust at sometimes up to 100, same amount of time. And then in South Boulder, same story. They were all gusting extreme gusts for about 10 hours. East to west, so we're showing the same, this is the same sensor, the extreme wind at Colorado 93 and 72 intersection. But note at my house, which is 4 miles east of there, which was placed right on as the ascending branch of the rotor, winds were much more erratic, still reaching about 70 miles per hour and still gusting quite a bit out of the west, but not quite as strong. And then when you go 4 miles east of there, that's when on the other side of the rotor, east winds, gusting 20, 25 miles per hour. And for a time there, almost nothing at all after about noon. No gusts at all, just almost light and variable. That's the anatomy of a mountain wave and the type of scales we're talking about in terms of where the strongest winds are versus where it's light and variable. So obviously played a major role in the fire. Once the fire got to that east side of the rotor, or underneath the rotor, I should say, it didn't have much wind to work with. All right, final thing to show what the rotor looked like. This is a radar loop with velocity on the right, reflectivity on the left. Ignore the time. Hopefully this starts at the beginning. Yeah, right before the fire starts. And so focus on this area where the fire starts. You'll see the smoke plume show up. So there's the smoke plume. These velocities are actually correct, and they fold over a couple times. But you'll note over the Marshall fire, it's consistently saying inbound in that smoke plume of about 60 to 80 knots. That doesn't move throughout the entire loop. You'll also see downstream, there's some outbound. That's the east, right underneath or just east of the rotor, which obviously helped firefighting efforts once the fire got into that general region. But the amazing thing is this couplet, the real strong inbounds and then weak or even some outbounds, doesn't really move until the evening hours. We're just now getting to 6 p.m. The fire's still going really strong in Superior and parts of Louisville. Finally kind of breaks down there. You see the real strong inbound. So the mountain wave finally broke down or evolved east, and there are actually stronger winds east of US 287 here. But that didn't happen until about 7 p.m. Just fascinating radar. I'll play that one more time just to give you an idea. It was picking up on those extreme winds. Right there where the fire was. And the wave couplet. Didn't really move. Never would have seen this otherwise without smoke, because this time of year, late December, there's no bugs, there's really no birds either. We would have never have seen the mountain wave show up on radar like we do now. Okay, let's move on to what our office operations were like. All right, so the DSS, starting with pre-event on December 28th, because models are really good at getting flow aloft and the strength of the flow aloft days in advance. So clearly it was easy to issue a high wind warning for the higher elevations in the foothills. Again, this was when we weren't sure how far east those winds were going to go, but it was clear that they were going to be strong enough in the higher peaks and ridges west of Boulder. We also had a winter storm watch in effect because it was going to snow once the main part, the real much stronger trough arrived, providing the first snow of the season. So we were worried about that as well. Looking at the ECMWF Extreme Forecast Index and shift of tails, I mean, it shows a little bit of a signal, especially up in Wyoming, but not much over Colorado for extreme winds. Again, that's not surprising at all that the European isn't quite high enough resolution to hit these mountain wave events with a whole lot of accuracy. So then the day before, so on the 29th, we did a DSS packet highlighting the wind and snow, elevated the watch to a warning. We updated the DSS packet at 4 o'clock, and then we issued a fire weather outlook that highlighted the elevated fire weather concerns across eastern Colorado. The day of the event, very pleased with our forecasting team expanding the high wind warning to all of Boulder County by that morning, just based on, and yeah, in the AFD and talking to the forecaster, they really pinged on the HR's consistency, bringing those winds east. So all of Boulder County, that whole corridor was under high wind warning 3 a.m. Did social media posts on that, emailed a new DSS packet by 5 a.m. We found out that, or we confirmed with Boulder County that if a high wind warning is issued, it doesn't matter what time of year it is, there's a burn ban countywide immediately. They do it right away. So not necessarily a need for a red flag warning based on that, but we'll talk a little bit more about a red flag warning, whether, would that have made any difference? 7 a.m. on the event, we were focused on the winter weather because there wasn't a fire yet. I mean, we get strong winds all the time here. 100 miles per hour is a little extreme, but winds are normal in the winter. In fact, they peak in December and January. So we were really focused a lot on the next day, first major storm of the season. Updated the grids, especially to increase the winds, because by 8 a.m. we were getting strong wind gusts all across that area. Then by 11 a.m. there were multiple fire starts, and so that was our first briefing to Boulder County Dispatch about those fires. And then the Marshall fire really got going by 11:40. Just before the fire start, the winds were getting all the attention, as they should have, with gusts to 105 miles per hour at the famous wind sensor at Highway 93 and 72, updated for 110 miles per hour. Then Bruno looked out the window and saw that. This is from our office window, and it was well before it was visible on satellite because it was pretty small at the time. We sent this tweet out. There weren't any evacuation notices at the time, even though 40,000 people did evacuate that day. And from this time, it spread 2 miles to the edge of Superior, where that urban wildland interface is, all in about 30 minutes. That's how quickly it was moving, given we saw the fact that it was gusting to 100 miles per hour throughout that entire time period from 11 to about 1 p.m. We offered to send a civil emergency message. Boulder County didn't take us up on that offer, but we were ready to do it. And here's Bruno's video. This is what it looked like from the office. Just a quick, he did it for social media purposes, so it's only 3 seconds worth, but that gives you an idea. It was not that far away. And Bruno will tell you that he knew and had that sinking feeling that I'm sure many of us have had when we know people could die from this. A fire like that in 100 mile per hour winds, with how dry everything was, it was going to spread, and it was going to spread fast. into populated areas. And so he knew it was bad by this point. The whole office knew this was going to be a life-changing event by that point. So here's a little bit on red flag warning. The red flag conditions weren't forecast nor observed. We were pretty confident they were never going to be observed from this. But that does beg the question, could we have improved our fire weather messaging if I mean, we know, any meteorologist would know, if it's been that dry and winds that strong occur, put a fire in that environment, bad things are going to happen. So is there a better way to do it, or can we be flexible on red flag criteria? That is the question. We're all kind of wrestling over that with our partners in the state of Colorado. But just for bookkeeping, our criteria is less than 15% and gusts greater than 25 for a 3-hour period. So the relative humidity actually never dropped below 20%. We knew it wasn't going to drop below 20%. Temperatures were in the low 40s throughout most of the event. So some ideas that we're working with, really highlight the fire weather potential in a high wind warning, do partner specific briefings so we reach the most important audience with what our concerns are. We might explore a sliding scale for red flag warnings, especially on days like this. We certainly could have talked about using the particularly dangerous situation red flag warning that was pioneered in California during their big fires in the last couple of years. All ideas that are on the table that we're going to work with our partners on. During the event, we did a lot of safety and evacuation tips. That actually took up a lot of our time, and it was time well spent because people were really glued to our Twitter feed during this event. People that weren't following the city of Superior, city of Louisville, and other emergency management entities, they were following us, and so they're getting information that way. Because this was out of season, this was not in the densely tree populated area of our foothills where fires are common and everyone that lives there understands the risk. This is an area that hadn't really seen a fire before, particularly a wildland fire. A neat tool you might be interested in is the wildfirerisk.org. Bruno grabbed these images of the Front Range of Colorado where risk to homes. I just mentioned the foothills. I mean, that's all big fires in the state of Colorado. A lot of them have occurred right along the Front Range here in the populated foothill area with lots of trees, lots of grasses. Further east, once you get out of the foothills where the fire started right around here, there is a risk because this is all grass area and they don't mow the grass. They don't maintain the grass. They keep it as open space because that's what is preferred out here. And right along that interface, it's still a pretty high risk. The city of Louisville itself is a low risk, as you can see plotted on this map. But that's a neat little tool if you're curious about what the wildfire risk is in your particular CWS. Is a neat thing to look at. Social media demand became unsustainable after a time with all the evacuations and urgent messages coming through, like this one from Superior that we amplified. So teleworkers, because we were still this was still right in the kind of the heart of COVID, really. We delegated that to the teleworkers and they did a really good job. They were listening to the police scanners and fire scanners and just monitoring the situation. Whenever Boulder OEM, the town of Superior, the town of Louisville sent a tweet like this, we would amplify it by retweeting it. We still kept up with the safety messages and what to do, what to plan for, because there were pre-evacuation notices for a lot of people. Yes, 40,000 did evacuate, but it was much more than 40,000 that needed to go at a moment's notice if they were ordered to. So all these social media posts, what to put in your go bag. We also provided weather updates, amplified the messages, and all of these pre-established safety preparedness resources. We were hitting it hot and heavy there. We sent 40 total tweets during that event with over 3 million impressions, over about 4,500 retweets. And as I mentioned, Louisville and Superior, the two cities / towns, whatever you want to call them, I mean, there's a couple 100,000 people total when you add the two up. They had almost no followers. So how were they supposed to get the word out to their people to do evacuations or at least amplify that message? We had that pull. We were able to do that. We're in a very unique position to leverage that. During the event, media interviews started to ramp up, especially there are lots of national ones, as you can see here. We designated a PIO, which at the time was the MIC and WCM kind of a tag team on that. We developed a talking points document just to keep our story straight and keep messaging on point. By the afternoon, the partner calls were just getting nuts, which they should be. We were supporting that because it was such a fast evolving situation. We provided verbal and or video briefings to all these different municipalities during the event. FEMA was quick to mobilize. Even just a few days later, the management team here met with the FEMA director and Boulder Emergency Management, shown here. We were collaborating very closely with FEMA in the following months, and it was a crazy day, but our job really did just begin that day in supporting efforts of the cleanup and recovery phase. So through the 7th, we did twice daily spot forecasts. We did daily briefings to the Boulder EOC. Continuing through February, we had a daily morning briefing to FEMA and the Joint Field Office. So two briefings a day through February. And then through April, it was a twice weekly basis with the JFO and FEMA. So lots of recovery support throughout that time. All right, Greg, I'm ready for questions. Again, wish Bruno was here to present that. He would have done a much better job than I did, but he is doing his thing as an IMET. This is from his apartment. He actually did have to evacuate. The fire got awfully close to his apartment complex in Broomfield, and then 24 hours later, it did snow about 8 inches. So even throughout the event, we were worried about the first significant winter storm of the season. It was fascinating.